Okay, so today we'll study cryptographic hash functions. All right, these are the references. Lovely video by Professor Christoph Parr at this place, and there's another good video by Professor Mark Stamp. Okay, so you can use any of one of these. Okay, so what we did in the last class? Where are we now? So we have still Alice and Bob. Okay, they are trying to communicate over internet or insecure channel. All right, this is a problem, and they want to not anybody know what exactly is happening, so they want to have confidentiality, integrity, and authentication, and of course availability. A usually stands for authentication. So we'll talk about availability later. So what we have focused so far, we are still talking about confidentiality, and confidentiality can come only if whatever Alice is sending to Bob, if intercepted by Mallory or Eve in between, she will not be able to make out what she is sending. Okay, that's the challenge that we are trying to solve, and one method for that is symmetric encryption, right? Okay, wow, this pen stopped working. Just a minute, give me a minute. Does lost contact appears. Just give me a minute, I will disconnect and connect again. Well, anyway, it's gone. Just a minute. Maybe charge is gone. Just give me a minute. Hello, folks. Can you see the PPT?
Yes, sir.
Okay. I'm sorry. Lost some time in my iPads got stuck. Okay. So we have been talking about Alice and Bob trying to communicate to each other over internet, and then we need to solve this problem: confidentiality, integrity, and authenticity. So far we have solved the problem for confidentiality where we are using symmetric key encryption. All right, so we have last class we have studied about this modes, because if you see divide the message into a number of blocks and then encrypt that using AES or DS, then it leaks information, which is ECB mode. Then we came out with CBC mode and C mode, and then we have of these modes, right? This is most okay. So this is where now we completed this part. This is where we at this moment in the course. So now today we'll start with the hash function. Okay, let me. Okay, all right. Okay, so what is hash function? We already studied a little bit about it when we studied password hashing. This is very important cryptographic hash primitive. Okay, and hash is digest of message. When we say digest of message, what does it mean? It means that input could be anything. Is input arbitrary length string? It could be anything. It could be, you know, your message that I like you, or it could be very long letter you write to your mother. It could be anything, or it could be a novel, or anything. okay, it has m bits, and m could be very large. Oh, sorry. It's a message m and can have large number of bits. Say, okay, it could be anything. If it's a n bits, then m can be anything. Okay, but output of this hash function is always a string of fixed size string, and this fixed size depends on what algorithm you're, whether it's 28 or 256 or something like that. Okay, so this we call as a hash of input string. Okay, or it's a digest of a message. It's a short but fixed length string. So input could be, for example, your file of 1 megabyte, but output of the hash function, when you pass this through a hash function, output is always a fixed size string, which could be say 128 or 256 or whatever algorithm you're using. Okay, so but this is a fingerprint. It means that is a unique representation of message. What does it mean? If you change message m slightly, then output will differ. Okay, if you use the same message again and again, then output will remain the same. Okay, so can you see here that we are not using key here? In encryption function, we have used, this was input and output was encryption of input, whatever, based on the key k. Okay, and we said that key has to be unique because this function is known to everyone. So here in hash function, there is no key, and hash function functionality is known to everyone. Everyone knows the algorithm. Then the question is, how do you use it then? Okay, so hash functions, we'll see how to use it. We have seen in case of password, right? We are not using key, but it has very important property. One important property is easy to compute. Easy means it will take short time and always correct, but it is hard to invert. Its inverse is very difficult. Given you a string of 128 bits, which is hashed output, can you find the original string? Now this is not possible. Okay, that's the beauty of hash function. That's the reason we use cryptographic hashes in the password file. Okay, so important use of hash function, we'll study digital signature, hash max, and of course hash passwords. Okay, all right. So we can define now hash function is the function which takes input message m, okay, which can be of arbitrary length, it can be of any length, but output is fixed length always of n bits, small n bits, right? So you can show this by the mapping here. Now note that here one in curly bracket we say the string which consists of 0 and 1, and you can see star here, it means that it can be of any length, but output is always of string with length n. So what are the properties? It's a deterministic, means that every time you input one string given one hash function, okay, one string you give input to is, say I like you. The output is of say 128 bits, fixed size. You do it something, so it's a string of zeros and ones. Second time you do, you get the same thing. Third time you always give this input, is you always get the same thing. Okay, so it is a deterministic and correct. Second is efficient to compute it. The whole process should not take a lot of time, otherwise unusable. Third important property that we have seen is one-wayness. You can, from this message you can get this one, but given you a hash of some m, if They ask you to find M or this message, I like you. It's impossible to do, right? This is called one-wayness. It's called pre-image resistance. Okay. Second thing is a collision resistance, which we'll study later. Okay. It's impossible to find two strings like one is like I like you, second is whatever, and both will hash into the same output. It's very difficult to find. It's almost impossible to find, right? That's called resistance. And the last one that, you know this message M, but can you predict what should be output here? No, you cannot. You know, I mean, a normal thing, but without using machines, you cannot predict, right? But although it's a deterministic, it means that looking at this output, can you find out what should be input like, you know? So the output has to be random or unpredictable. So these are the property. Basically, if you change it in the input here, output will change. It output will totally differently. We'll come to this point little later also when we look at the example. Any question up to this point? No? Okay. So let's repeat what we have studied. Output of hash function is always fixed length, is independent of input length. So practical hash values are 128 to 500 bits depending on the what hash algorithm you are using. Okay. And then computed hash output, which we call as fingerprint, should be highly sensitive to all input bits. Okay, if we make very small change in the original message which we are hashing, output will change in many bits. Hash value, it means many bits of hash value will change. And there is no detectable pattern how output changes based on a specific input changes. Okay. So any changes to message M, that message M is one which we are hashing, will change the resulting hash values in seemingly random way. Okay. And of course is unkeyed. So if it is not keyed and hash function is known, then anyone can use the hash function. And that's the reason we have seen we can do random, you know, brute force attack in passwords, because everyone knows the hash function and you generate all possible values of combinations of passwords that are possible using dictionary or whatever, and then create and compute hash value of that and compare with the hash password you have got through a password leak. Okay, that way you can find out, but inverse is not possible. Given somebody has given you a hash password of somebody and ask you to find out if inverse function to get the original password, it's not possible. Okay, now this point, look at this diagram. Message, this is the same hash function we are using here. In the first message is this one. Alice was beginning to get very tired by sitting by her sister on the bank and having nothing to do. Second is I am not a crook. And third one is I am not a cook. And output is this one for the first case. Note that output size is same. Number of bits here will be same in all three. But compare these two. What is the change between the two inputs? Only this letter R is different, right? There is no R in the third case, right? So it says I am not a crook. Here it says I am not a cook. But output, you see the difference in the output, it totally changed. Okay, now looking at these two, you cannot find out that there is only one character change or maybe one bit change between the two. Or there very minor change between the two. All right, any question? Okay, so let's move ahead. So just remember, it is difficult to construct a text given a hash. So reverse function is not easy. It means given h of m, it is the finding m is very difficult, very hard. So in polynomial time you cannot do this. There's a message. Okay, it is difficult to modify given text without changing hash. So if you change m to m dash, okay, then h of m dash will be different from h of m. It is difficult, again, it is difficult. It's not impossible. Okay, it's not impossible, but it's very difficult for anybody to do that in constant time or polynomial time. So it is unlikely that two different messages will have same hash. Now, why we are saying difficult? Why not saying that it's not it's not possible at all? We are saying difficult, right? Because there will be some clashes, right? There will be some collisions. But finding out, see, there will be some value of m and m dash, both given to h, will result into the same output. There will be some, because ultimately we are mapping a large space into a smaller space, right? Smaller space is just 128 say bits. Larger space could be anything. It could be, combination of 1 million to raise power 1 million. Okay. All right. Okay. So what is the, how can we use it intelligently then? Okay. We can do document comparison. So Alice and Bob both have a document, one document, and they want to make sure that the document is the same. Okay. So it's 1 GB document which they cannot easily transmit over very slow speed internet, right? So they cannot. And ultimately, even if they are able to transmit, they have to compare. So instead of that, both can compute hash over the document and then communicate hashes to each other. Okay, and then both and Alice compares the received hash with the hash she has computed, and is the same, then she will be sure that both documents are the same. Okay, now let's look at this thing that we already discussed, that original message could be of any length. So this space versus output is n bit string, the space here, this is very big in comparison to output space, right? It means that all the possible combination of here will be nothing but, if it's n bit string, n bit output is a 2 raised power n possible combinations, right? Where here it could be of any size. So it means that there will be many such messages which will be mapped onto the same output, and that's called, so basically this is a large domain to a small domain. When you are mapping, then there will be some collisions, and the compression we call is lossy compression. So collision is that for h of x, or we calculate h of x and of h of x dash, if both map to same y here, then we say there is a collision. Okay, all right. So what are the properties of hash function? We have already seen first function property, one-wayness, or that we call is pre-image resistance. Given an output y, which is nothing but h of x, it is infeasible to find any input x such that h of x is y. Okay. So given you some, okay, h of x, you calculate, somebody calculates this, someone, Alice, for example, calculates h of x. She knows x and y. This is output y, and she gives to Bob. Bob has value of y. Can Bob find out value of x from this? No, it is not feasible. Okay, so reverse mapping from the digest or hash output to original message M is not feasible. Now, when we say infeasible, it means that it is in polynomial time. Okay, all right, okay. Same thing we have shown it here. So please go through. Now, of course, this can be broken, as we see in case of password, by brute force attack. For example, Bob wants to break this, finds a value of y, x, then he will generate all possible values of y. I'm sorry, given y, given y, all possible values of inputs, and apply to that h function. And then when he finds out that h of say x dash matches with y, then he's got the answer. Okay, that we have already seen in case of when we do attack on password. Okay, second property is called, so first is inverse property. Basically is a one-way property that finding inverse is is infeasible. Second is collision resistance. It means that, okay, it is for two different inputs, output is the same. So it's difficult to get a pair of inputs x and x dash such that they output into same hash value. Okay, all right. So, okay, just a minute. Let me make my mobile into sleep mode. Okay. So we can say that give the definition of collision resistance as follows. It is infeasible to find any pair of x and x dash such that x dash is not x, such that hx is equal to hx dash. It means that x dash and x, it could be any two strings or inputs, it could be any two in the whole domain, and both map to the same output y using h function. Okay, so we say any pair. Note that any pair, it could be anything, anywhere. You have to find any two. Now, property says that it's infeasible to find out. If you use computer and try to find out any two values, that maps into, given you a hash function, that maps into same y, same value of y, which is h of x equal to h of x dash in polynomial time. It's not feasible. Okay. Now, related property is that second pre-image resistance. So given one value of x, now in the whole thing we have one string x, okay, and h of x is y, okay. You have to find another value. Given this value, you have to find another value x dash such that h of x dash also maps into same y. All right. So this is a hard problem. Any question? Please go through it. You will understand it. It takes multiple times reading to understand this. Okay. Now you will see that this input side is could be of any length and output of fixed size, so there will be collisions. Okay, all right, but it should be very difficult to find out the collision. That's the property. Okay, so if let's assume that this output string is 128 bits, then input string is let's assume we consider input string is of size 150 bits. It means that 2 raised power 22 such strings will map into same output. But finding that is difficult. That's the crux. Okay, all right. Now let me ask you this question. Okay, so all of us have birthday, right? The date we are birthday in a year, right? Okay, what is the probability that at least 2 people in your class will have birthday on the will have the same birthday, and this probability has to be greater than half? What is the probability? How many people you need? What should be class size such that at least 2 people have same birthday with probability greater than half? Any guess?
Sir, around 76.
Around 70. Okay. Yeah, good, very close to answer. All right, you can calculate this. Okay, now why we are doing this? Most people answer 183. The number of days divided by 2. It is very intuitive answer, but it's incorrect. Okay, you can calculate this, very simple, right? The first person, let's assume you're the first person who's joining the party. The probability that no one has collision, you don't have collision with anybody else, is 1, right? Because you are the only person. The second person joins, the probability that he has no collision with the first one, 364 by 365, which is equal to 1 minus 1 by 365. Third person joins, it means that that person doesn't have collision with anybody else. The probability is this one, right? And you find out for n number of people, so this is the probability. Okay, and equate this to half. Okay, because the probability has to be greater than half, greater than equal to half, and solve this, you will get n is equal to 23. If you have class as 23 people, then there is a probability greater than half that 2 people have same birthday. So now your class is now if you increase this probability 0.5 to say 0.9, then you will also need more number of people to have birthday with the probability that 0.9 that 2 people have birthday on the same date. So it should be 70 or 80, something around that. You can always calculate that, right? So I'm sure in this class 100 plus there will be many students who will have same birthday. Is there somebody you know among your friends? Do you know or you do not know? So why are we studying this here, birthday problem? Because we are looking at the collisions. Okay. Now look, so approximately we can say that, okay, but hash function here, we are looking at 365 days of year. Okay, the output could be, output is birthdays, which can be just 365. But in our case, the output is of size n bits. So it will take 2 raised power n. The 2 raised power n values are possible. Okay. And so this answer that we have got here, 23, is approximately equal to square root of 365. So we can say that square, okay, if you hash about so many square root of 2 raised power n times, then you expect a collision. Okay. So basically you'll have to now work to, if you want to break this, then you'll have to have at least 2 raised power n by 2 attempts with different combination to break it. Now question is that what is this 2 raised power n by 2? Okay. What is n? N is the size of output of the hash function. Larger the value of n, this value is very high. Okay. Now if this, we make this as 128 bits, then through brute force you'll have to have so many attempts or combinations, a number of messages you need to generate to find a collision. Is this a big number? 2 raised power 64? Yes, it's a big number, right? Is it a big number from today's perspective? I mean, look at number of kind of processors we have. Yes, it is big, but it is found out that 128 bit is better to use 256 bit message or even longer than that. Okay. All right. So one property that we'll see in hash function that we need to design is called avalanche effect. So it means that if you change 1 bit of input, it should affect at least half of the output bits. We have seen one example in the past, right? Okay. Now, like we have seen in block encryption, here also hashes, we'll have to break the message into blocks and then hash them to find out the final hash. We'll see the design in the later class, maybe tomorrow. Okay. This one property which is we have studied already, one-wayness and collision resistance. Both of these properties we studied. So note that one-wayness does not imply collision resistance. One-wayness simply says that given one output, hash output, this h value or hash value, it is difficult to get m. Okay. Collision resistance does not imply one-wayness. It simply says that we will have to find m and m dash such that they result into same value of output, which is h or y, whatever. Okay. Okay. There are any application of hash function that requires only one-wayness. For example, passwords. Okay. All right. Although it may, there are a lot of properties are there of hash function, but one-wayness is most important property for passwords. Okay. Hashing versus encryption, what is the difference between the two? Hashing is just one-way function, while encryption is, you can have unique decryption of that encryption function, right? From given value of x, you do h of x, you get y. From y to x is not possible. Now given you value of x, you do encryption of x using some key k, you get y. Given y, you will have decryption function which will use y and key k and you'll get x. That's the difference. Okay. Now if you, since there is no key, you hash this multiple times, you get the same value. But in case of encryption, if the key remains the same, output may the same depending on value of IV. Okay. So if the key changes for each time you do encrypt the same value of x, then output may differ. All right. Now let's come to hash function types. We'll just briefly look at it and later on we'll discuss this. There are two types of hash function, which is dedicated hash function. It means that these hash functions have been designed. You develop an algorithm and hardware to do hashing. This hashing, right? cryptographic hashing. And secondly, use the block ciphers that we have discussed earlier to do hash, to have hash function. Okay, all right. So we'll focus on, we'll not go into depth of these designs. We'll just briefly look at it, how it works. Okay, we have looked at how AES and DES works. Okay, note that in AES, DES, size of input and output of from encryption and decryption is the same. Here, input size is could be anything, but output is always fixed. So that's the difference, right? Okay, but lot of things are common. Okay, all right. And all these are public knowledge, right? So all these algorithms are public knowledge. So MD5 is, or MD4 family, sometimes we call it MD5 family, is the most common one, and components of that or various algorithms within this family are SHA-1, SHA-2, and SHA-3, and RIPE MD160. Okay, so we'll look at some of these in very brief now. MD5 has output of 128 bits and is completely broken. Okay, then SHA-1 is output of 160 bits. The hash output is 160 bits, is completely broken in 2017. SHA-2 is something which has output of 256 bits minimum. Note that the length is increased, right? And we have seen as the length increases, someone if wants to break it, brute force has got to have so many combinations, 2 raised power n by 2. So 2 raised power 128 values he or she has to generate to find out a match, and which this is very large number. Okay, so it's not broken. And the next one, which is called SHA-3, which is called KCAC, which is very similar to SHA-2. Okay, there have been one attack which is called length extension attack. So it's as follows, right? We'll not go into details of this, but it works as follows, right? Given message M1 and M2, where M2 is nothing but M1 concatenation with X. Basically take M1 as a string, 0 1, and add to that or concatenate it with another string, join it with another string. This is called concatenation. So this is initially M1 concatenated with this string, which is X. So this overall becomes M2. Okay, now given you value of M1, H of M1, sorry, H of M1 and X. Given this, can you find out H of M2? Okay, if you can do this, you have done a successful attack. Now, this kind of attacks have been possible in hash functions. All right, so, but this does not violate any property of hash function, but is undesirable in some circumstances. But this kind of attacks are possible. Given you a hash of something, okay, and the length of X, but not X. So X is not known. Given X and length of X, then you can create H of X with some, so basically H of X concatenate with some value of M, okay, and which where M is of attacker's choosing. Okay, so basically from H of X, somebody can create H of X plus M, or X concatenate M. So say for example, initial message is I am a good boy, and H of this is known to some string whatever, and then from now you want to create this, I am a good boy and smart. This is the first string as it is, and you say that smart and smart. Then from this output, which we have generated earlier, can we create hash of this without knowing anything about it? So basically, given this, can we add small string and then get hash of that? Okay, so that's the, so it may not be desirable in many cases. Okay, so what do you think? Is cryptographic hashes give you integrity? Anyone? Does any function, does it provide integrity? When Alice and Bob are communicating, can we say that they are using cryptographic hash? The message that Bob receives is whatever Alice has sent. Mallory cannot change it. Can you say that? Okay, Alice is sending a message M to Bob. In between there is Mallory. Okay, so Alice computes M on an H of M, sends it to Bob. Bob receives M. Bob receives some message, say W and H of W. Okay, can you be sure that it has come as it is, not being changed in between? Okay, tell me.
If they change the hash only, then it will not be integrated.
Yeah, repeat.
If the
Yeah,
hash
good.
uh, if the hash part is changed, then it will not maintain integrity.
Now, how does he know the hash part is changed? All he received something and he will calculate hash of that because he knows the hash function, and that looks fine. He will receive W and some hash function, so some hash value. He receives some W and say X. He receives W comma X. Okay, what? How does he know this is correct? He will calculate H of W and then compare it with X. If both match, then can he say that it has come from Alice? No.
No,
Okay,
sir,
so
because
we huh?
two messages can have the same hash, right?
Yeah, no, the two messages cannot have it. The collision is not possible. We have studied that, right? In polynomial time, you cannot create something is similar but have same hash value. No, what happened that Mallory in between intercept this messages, changes M to say W and calculates H of W and sends it to Bob. Can Bob find out it's not this? It's a manipulated message? No, it cannot, right? This is called man in the middle attack. Okay, so it means that we'll have to use cryptographical hashes very intelligently. So it depends on your threat model, whether it can give integrity or not. For example, Mozilla publishes new version of Firefox. Okay, and it generates binary, right? Mozilla will never give source code, generates binary. You download the binary. Okay, how do you know it's genuine binary? We normally don't do it, right? Now you go to some websites. Okay, you'll find they have also published hashes. Did you find it out? For example, the assignment you have got when you're downloading something, say virtual machine, they would have also given in the website the hashes of that binary. So what you do is that you download the hash also, and then when you get binary, run the hash function and calculate hash value of that, and if matches with the hash that's published on the website, then you are sure nobody has in between has tampered with it. Because your message may be coming through many routers, somebody would have tampered it, right? All right. So here the assumption is that the attacker cannot modify hash on the website. Okay, then hashes will work here. So in the Mozilla side, you will get binary file and hash value. You calculate, you download the binary file. Okay, it may pass through Mallory and Eve, maybe a router or some software and router, and then when you receive the binary, what is the hash function that's used, because it's also published. You calculate the hash on that binary, which say h, and then something which is maybe k or something published as a hash value of this binary on the website. Download it, then h, if h is equal to k, then you say everything is fine. Now probably this all works if Mallory is not able to change the value of this hash in the website of Mozilla. Okay, all right. Another scenario we'll take. Now, Alice and Bob wants to communicate with insecure channel. Mallory can tamper with message. This example we have already discussed, right? So if Mallory can in between change the message and the hash, then there's no way Bob can find this out. Okay, all right. Okay. Now note that a lot of limitation of hashes come because of the unkeyed function. All right. These are the uses. Little later we will study how we can have message integrity. We will study digital signature. We have already seen hashes are used in storing password, etc., etc. Okay. So please go through this attacks on hash functions. In the next class we will look at. Please go through all this. We'll look at some of these things we have already discussed, but we'll look at some implementation of these in the next class. Like how do we implement these hash functions? Okay.
So for the assignment, it is given that we have to download a virtual machine, but can we use WSL as well?
Okay, just a minute.